In the video on testing your model, we showed you a simple way to use the same sample set for training and testing in order to measure the performance of a model. But there we tested the model on the same data on which we trained it, which is much like giving a student all questions of a test before testing them. Measuring the performance of that student this way is not going to help us if we want to know how well they'll do when they're asked to answer questions they haven't seen before. After all, that is what we are really interested in. What we could have done instead is to give that student 80 example questions of our 100 available ones, and then also test them on 20 new questions which they have not seen before. Or even better, if we want to make sure that our selection of questions has no effect on their performance, we should do this multiple times. Of course, using different students would mean changing the boundary conditions, and hence we would need to reset our single unfortunate student's memory before each run of the test. The two methods described are called split validation and cross-validation, and we will talk about the latter one, cross-validation, in this video. On the screen I have the process 04 testing the model open and displayed. If you want to follow along, you can download the data file and processes which we are using and import them. The data loading process video will show you how it's done. Now let's go ahead and get started on the cross-validation. First, let's get rid of everything after the filter examples operator by dragging a rectangle over them and then just hit delete on your keyboard. Then let's come over to our operator panel and search for cross-validation. So let's drag that over here and let's connect the ports. Before we dive into what we need to do with this validation operator, let's talk a little bit about what cross-validation does. If I look at my parameter panel over here, I have something called number of validations. The default is 10. So what does that mean? Well, when I have the default of 10, it will take my data set and break it into 10 smaller subsets of data. And then it will go ahead and build a model on 9 of those, keeping one of them for testing, and then it will iterate. Sounds confusing, doesn't it? Well, let's take a look at the image here, which will help us to clear up some of the confusion. In this particular case, we have a data set that has 5 cross-validations. So you can see here 1, 2, 3, 4, 5 iterations. And so what the cross-validation does is it breaks the data set into 5 subsets, trains and builds the model on 4, and measures the performance on the 5th. Then it iterates. It selects another 4 different ones, and selects another separate test data set, and then builds the model, measures the performance, and finally begins to average that. So it'll do that over the entire 5 or 10 or however many validations you set, and give you an average performance of the model. So let's switch back. Can you see the little blue hierarchy symbol? Whenever you see that on any RapidMiner operator, it means that there's something going on underneath the hood. It's a subprocess typically. So double-click on that. Okay, now we actually have 2 new windows. Do you remember how we talked about training and testing our student on different subsets of questions? In the subprocess of this validation operator, I have a section for training and I have a section for testing. So the left window represents what we have in our testing model video in the upper branch. You've also seen this brief when we started this video. Since this is the training area, we clearly need to put our decision tree model in here. I'm going to pass my data, my training data, to this decision tree and build a model from it. So I'll connect the mod to the mod port. On the right-hand side, we will do our testing, and for that we need to apply our model to our testing subset and measure the performance. Let's pull in our apply model operator and also the performance operator. So before we make any of these connections, let's talk a little bit about them. Here in the training window, we create the model. Since we want to apply it, we need to feed the information about the model into our apply model operator. Now we need the unlabeled test data to which we want to apply it. In our 04 testing the model process, this came initially from the multiply operator. So where does it come from in a cross-validation? The copying or example selection of the test and training subsets is done automatically and represented through the 2 windows. And we can get the test example set here from the TES port. So let's connect that and then send our now labeled examples to the performance operator. And finally, since we're doing multiple iterations in a cross-validation, the PER port of our performance will go to the PER port to build the average of the different models' performances. Great, now we're almost ready to run the model. Let's go up 1 level outside of the subprocess, come back here to the validation operator, and connect the PER port to the results. But before we run the process, why don't we save it first? So let's go to our repository to the left, highlight Process, right-click, Store Process here, and let's call it 05 cross-validation. Now we can click on the Run Process button. Okay, these are the results. Well, what you see here is a confusion matrix, so no wonder we are a bit confused. Okay, that was a cheap shot. But once you know how to read it, then it's quite simple. Let's start over here with the accuracy. The overall accuracy of all predictions achieved by the 10 models, each of which made a prediction of 90 examples, after being trained on the other roughly 800, is nearly 84%. That is the percentage of correct predictions. The plus-minus is one standard deviation, which is calculated from our 10 individual model accuracies. The lower this number, this is a critical, important item to note when you're evaluating your model. The smaller the one standard deviation value is, the more stable is your model. A stable model, given that it has a high enough accuracy, is good as it will give you a smaller range of best and worst cases which you have to consider for the quality of your predictions. Now let's take a closer look at the table. PRED.loyal stands for predicted loyal. PRED.churn stands for predicted churn. Now, if you look down the columns of the table, you can see what labels we had in our example set, and then if they were predicted right or wrong. So we had a total of 509 plus 69 loyal candidates, okay? And when we ran the algorithms through, they predicted loyal 509 times, which are actual true loyals, and 69 times it predicted churn when in fact it should have been a loyal. In total, we were able to capture 88% of our loyal cases. For the churn cases, we achieved 76%. A really handy way to look at it is to look at the diagonal which shows the true loyals and the true churns that were predicted correctly. And now you can see how the overall accuracy which we first talked about is calculated. It is the total of correct predictions, 509 plus 246, given as a percentage of all 900 predictions. The last thing to look at is the class precision, which shows the percent of predictions that were correct for each predicted label, loyal or churn. So if you want to calculate that for our churners, you simply add 69 plus 246, and then divide 246 by that sum to get 0.78 or 78%. Now, if we interpret the table with focus on our churners, then we can say that we are currently managing to predict 76 out of 100 true churners. On the other hand, in 22 cases out of 100 churn predictions, we label someone as a churner who is in fact a loyal customer. And that's it. That's how you can effectively validate the model and see how good it is before you take next steps to improve it or decide to put it into production and deploy it. Thank you very much for watching.